Thank you very much. Can you hear me without technology? Easier. Thank you. Thank you, Peter, and thanks to the organizers for the invitation to speak here. I will talk about NMR, as you know me might expect. NMR mostly, but I took the liberty to insert one topic which okay, simple thing, I'm talking about just polyelectrolytes in solution only. Simple idea, we have a coiled polymer. If hypothetically we would introduce charges on it, it would go into a stretched conformation. If I change something in the environment, in the solvent conditions, for instance, I add more salt, I screen some of the charges, or counterion condensation. Now I have to get a little bit technical in the NMR. The first thing I wanted to insert is a little bit about polymer chain dynamics. Use the transverse relaxation time to T2 to learn something about the polymer dynamics. So in general, we see, like for most of the polymers, in general, theoreticians will tell me there's a wide distribution of mobilities, but we can describe what we observe by two modes. There's one fast decay in the signal that we have, that is short relaxation time, that is indicative of restricted motion, as we have it, for instance, around entanglements. And then we have a longer decay, long T2, and that is the more free chains. Relatively smooth curve. If we plot it in a double logarithmic plot, then we would have like two straight lines. So we get two components, two relaxation times, indicative of the motion, and the part I'm also interested in is relative population. Which fraction of the polymer experiences some restrictions of the motion? So we do the experiments, polymers under shear. I copied it out of a paper on the polymer melt. So we have a Searle cell, double cylinder cell. We have the polymer. So now the polyelectrolyte solution in the gap between the cylinders. The inner cylinder is rotating. We get this like two-component decay, as you see it here, and if we have no salt on a polystyrene sulfonate, then we see as we increase the shear rate, we prolongate the relaxation time there, but that can be very different. So I now have the summary of the data because I just wanted to. On top, we have low salt, no salt conditions. We see that after a certain shear rate, we see that the fraction of the polymer that experiences some restrictions of the motion is going up. And that fits to the picture I've been searching on for a long time, that we have some partial alignment of the polymer mobility between the motion, between the chains. But we get a different situation if we go to a high salt condition, where we screen a lot of the charges on the polyelectrolyte. They get less stiff, more flexible, and then that this fraction that experiences the short relaxation time, the fraction that experiences hindrance of the motion close to entanglement is going down. That is indicative of losing some entanglement. Chains are flexible, they can be entangled, and then we even saw that for PDMS. Recently we have something published. That seems to work. Okay. Maybe. The other experiment I want to introduce is the pulse field gradient NMR experiment that is probing displacement. What we do is we have we excite our magnetization with one of the green pulses. After some time, we refocus the magnetization, and after the same time, but in between, we can apply some pulses here, some what I think are magnetic field gradients, and they label the position of the spins in the phase of the signal, as I have it simulated. If the spins at the same position for the two gradient pulses, we get a refocusing, we get a full signal back. The relaxation. If we have a random displacement, then we have not the same magnetic field gradient, same magnetic field from the gradient field during the second gradient pulse. Therefore, we have some residual phase errors, and if I integrate over the entire phase signal, that is attenuated, and from the attenuation, I can the situation becomes different when the spins move in the same direction, the same distance during that time. And the phase error for every spin package is the same. Integrate, I get a full amplitude signal, but I get a phase distortion. From that phase distortion, I can also work out the displacement. I know the time. So for the first case, just to illustrate it a little bit, we have here an example where we have water, we have a polycation, P-DATMAT, and we have glutamic acid here. We can identify them from their chemical shift in the spectrum. And from top to bottom, the magnetic field gradient is increased. I put it that way that we can see something. So the water signal decays at first. Because it's the smallest molecule, it has the fastest diffusion. With these settings, we hardly see any modulation of the polymer, and therefore we have. If I use this spatial camera plot, the logarithm of the relative amplitude over the square of some experimental parameters, I get a straight line for anything that is. Use that to look at the fractal dimension, for instance, of dendrimers and dendrons. If I look at a dendron of the polyamidamine dendrimer, then I get, when I look at the change of the hydrodynamic size as a function of molar mass, from the inverse scaling exponent, I get a fractal dimension 2. If I have a bifunctional core, I get a fractal dimension of 2.3. If I use what is the commercial dendrimers, the permanent tetrafunctional core, you can end up with a fractal dimension larger than the dimension. That's just one way I try to use sometimes dimension to describe. Looked at polystyrene sulfonate. I like it a lot. A strong polyelectrolyte. I can get it with a low polydispersity. I look at the hydrodynamic size as a function of the degree of polymerization. A straight line in this double logarithmic plot. If I add a little bit of salt here, then I get another straight line. What is different? From that, I can work out the fractal dimension. So for polystyrene sulfonate dilute solution in salt-free, I get a fractal dimension 6. It goes up to 8. With the higher salts, I use. So that is, I think, what many people can do, want to do, may do. The other thing what I like to do is applying, in addition, an electric field. That's why I was talking about the different signatures between random diffusion and directed motion. I struggled a little bit to get it really adapted to the aqueous system. That is a sketch of our experimental setup. We have this U-shaped tube. We have 2 electrodes inserted there, and I apply up to 1,000 volts into that. And that is not a lot in terms of the electrophoretic motion, but it's a lot for the electrochemistry that can happen. So we have electrolysis of the water. We have gas bubbles that come out, and with this design, the gas bubbles come out either on this wing of the U or above the sensitive volume. And therefore, I can measure in the green radio frequency coil, I can measure the displacement of the velocity and also the direction. That's important for what I'm trying to do. Pulse gradient NMR experiment, the way we do it, takes tens of milliseconds. On that time scale, with the voltages that I apply, I only see a steady state. Time ago, we spent some days in the lab trying to see some acceleration. We never saw any signature of that. So we get a steady state between the electric field pulling on the charged objects I'm looking at. It can be a molecule with condensed counterion, solvation shell, it can be complex. And counteracting, we have the hydrodynamic friction. Hydrodynamic friction is proportional to the velocity, so I can only accelerate until I have this force. From the force balance and some of the experimental parameters, I can work out the effective charge that is moving in that electric field. You see the charge that we get. I only have to measure in two separate experiments the electrophoretic mobility and the diffusion coefficient. Some arguments, some questions, I measure them on the same time and length. So for the chemists in the room, diffusion ordered spectroscopy is probably well known, DOSI. We correlate on the horizontal axis identifying what we're looking at, and in the vertical axis we have the diffusion coefficient. Here I have a polycation and I have and glutamic acid, roughly the same size. I cannot differentiate them, but I can differentiate them in the electrophoretic NMR experiment. OSI, mobility ordered spectroscopy. The thing is here I have the electric correlated with the chemical shift. I don't want to separate spectra, I want to get quantitative, but I want to show that I do not fitting or whatever, it's a straightforward. We'll transform to get. Okay, now maybe back to something I did some time ago. I have to say, kind of cheating, I don't need to do it anymore, but here we had polydatmac on the right side. On the left, we have the fluorine spectrum of fluorinated succinic acid. So if I look at the fluorine spectrum, I have the counterion. Look at it. Oh, sorry, that's the wrong way around. On the left, we have the p-datmac with a positive electrophoretic mobility and the succinic acid. It only happens if I look at them separately. If I really bring them together in my cell, then you see that succinic acid reverses effectively the electrophoretic mobility. It's after lunch, but if somebody dares to look very carefully, it's not exactly the same electrophoretic. So what we really see here is that it depends on the concentration of the succinic acid. There's only very little, and it has a positive electrophoretic mobility. All of it can basically condense molecule. If I had more, then I have a higher concentration, and I only see a weighted average between the free and condensed counterion. Basically, the same thing is visible in the diffusion experiment. I just think electrophoretic mobility is more clear, more obvious because I have this. Really, what I have is polymer, and I have some condensed counterions, but there's a change between the two populations of counterions, which are condensed and which are free. So I only see an average on the time scale of I go back to all the polystyrene sulfonate of different molecular weights, and yeah, for a monomer, I find a single charge, which is also nice. And the whole setup that we're using. For an octamer, I still see something roughly like 8 charges. If it's getting larger, I see a clear deviation. Accidentally, there is a range where the simple Manning theory would describe that, but go to a larger molecular weight, larger chain size, then the coiling really matters. I cannot describe it. straight rod. But if I add 5 millimolar salt, as I showed it before, then we also see that. Okay, I'm going to go Christian Holm and us simulated that, and we had these overlap between capillary electrophoresis and relations hydrodynamic interaction along the chain. Same thing basically is observed if we look at proteins. So we have various other proteins looked at. ESA, the simplest one to look at, is pH. But if I look at the titrated charges that we get, if we go to the high charge. Okay. Looked at variations of the ionic strengths. Maybe that's less interesting. We also looked at variations of the dielectric constant of the solvent. We mixed methanol and water, and that the effective charge is going down. There's one trend that we could predict again if we use the simple theory. We see this trend here, but we see rapid decrease of the electric that we have to look, we have to measure the diffusion anyway, and then we converted the diffusion data into the hydrodynamic radius, as you see it here on the right side, and you see there's a similar stepwise decrease in the size, so we have more coiling of the molecule, and therefore charges get closer together. And by a single goes up, and therefore okay, looking at counterions a lot, then I thought that must be also useful to look at something a bit more biologically relevant, but I still wanted to keep it easy. So we looked at a macromolecule, in this case again polystyrene sulfonate, and then we looked at lysine and vary the pH. Change the pH, and low pH lysine is positively charged. We have strong binding like a counterion. We have no binding. Not charged. That was the starting point of this investigation. Here we have a few points there. We measured on the left-hand side the diffusion coefficient, on the right the radii that we measured, and if we look at the mixture with the lysine and the polystyrene sulfonate, we see that we also get a strong deviation at the lower pH where we have a charge. And if we now look at the electrophoretic NMR, maybe again pure lysine, positively charged, polystyrene sulfonate, negatively charged, and we see as we bring them together. Roughly here, but maybe I look for a bit of a summary now. First, we looked at the Henderson-Hasselbalch equation and charge that we get for the lysine, just looking at different literature values for the KAs, and then we look at the bound fraction on the left axis, the red point. Converted it into the constant for the lysine. So there's a very small bound fraction at high pH. It didn't manage to get it to full 2 charges because to the very low pH. High there, but the key point here is if I draw this line where I have 0 charge in the lysine, I still see something like 20% bound, a fraction of 20%. Easy for me as a physicist to think about it. Only get to the state where I have no binding, no transient binding of the lysine to the negatively charged polyethylene. Generate some negative effective charge on the lysine. So there can be different reasons, waiting for other explanations. But it could either be that the dipole moment on the lysine matters. When it has zero net charge, then it still has some partial charge somewhere, or there's other interactions. I think with that, I'm a bit faster than expected. I hope I could show you that pulse width gradient NMR is very useful to measure translation of molecules in solution. We can separate coherent and incoherent motion. We can see counterion condensation directly, as we can observe the motion of counterions with charged macromolecules. If we know the effective charge of macromolecules, we can determine the degree of counterion condensation. So usually for strong synthetic polyelectrolyte, I hope I could convince you that we can use that also to measure transient binding with the information on the effective charge. Of course, I didn't do it myself. There was a long time collaboration or a number of people in my group who did some of the experiments. Some people helped us with some of the materials, and in particular, there was great support in our institute. Biological NMR, and on the proteins, I'm collaborating with Otto. And thank you for your attention, and I'm